Hello everybody, my name is Tyler Gitto, and today I will be talking to you about my research in investigating indium-tungsten-oxide, or IWO, properties for thin film transistor applications. Special thanks to Dr. Hirschman and Rishmi for helping me through this research and helping make these slides. They've been a tremendous help. So to start, we're going to talk about today's technology and what has been used for materials for thin film transistors in the past few decades in industry. We have amorphous silicon, LTPS, and IGZO. IGZO having the best mobility and uniformity ends up being the winner. This is because amorphous silicon has a mobility of less than 1, however, was heavily used in industry for a very long time until IGZO came around. LTPS was looked at for a very long time because of its extremely fast mobility, but because of uniformity issues, it was never really able to be produced in industry well enough that they'd be used for thin films. TFTs. So why IWO? Well, IWO is twice the mobility as IGZO, which is, like I said before, the leading material for thin film transistors at this moment. However, the material properties that we're seeing for IWO are promising enough that we think we can make a case that this could be a potential competitor for IGZO. So quickly, just to talk about amorphous silicon and IGZO and poly. Amorphous silicon, pretty easy to process, as well as IGZO. Again, having these lower mobilities restricts us in our refresh rate and how many pixels we can put on a display as we scale. Poly is just incredibly hard to process, even though if it's high carrier mobility, it just seems inefficient and too difficult to manufacture well on larger displays. So with that, let's start talking about IWO and what we're kind of doing here, and kind of give you a little bit of an overview on what we'll be talking about. So our target material is 98% indium oxide, 2% tungsten oxide, and this is a conductive target for DC and RF sputter. We're using a CVC 601 DC sputter tool, and the two ambient gases we're using for our experiment is argon and oxygen. Oxygen is typically added with sputtering metal oxides. This influences the material properties heavily, and we will find out how it affects the material properties later on. So the magnetron configuration creates this racetrack erosion due to the target being confined to the plasma. This is very normal in most sputtering cases to have this racetrack due to the electromagnetic field that creates the plasma from the target. The main thing to look out for is avoiding target surface contamination, and we investigate and figure out why exactly the erosion happens. What ends up happening exactly is there's different electronic behavior that comes with the target being poisoned, and we'll elaborate on that in later slides. Let's talk about our goals and objectives for this project exactly, because we ran into some roadblocks and ended up having to change a few things as time went on, because no research ends up perfect and exactly as you plan it to go, or it wouldn't be research. For our goals, we have established a relationship between the electrical and optical properties of the sputtered and annealed IWO films. Identify electrical and optical properties of sputtered films that support semiconductor behavior and TFT operations. To kind of double check our work with identifying the electrical and optical properties, concurrent work was being done by Rishmi in order to look at the sheet resistance between what she was getting in her thin film transistors and what I was getting with just my sputtered material on a wafer, where my wafers were half silicon, half oxide. And separate tests were done on both sides. One was for thickness and the other one was for sheet resistance. And the silicon side also, we obtained optical parameters from them and in K values. Talking about the objectives now, we trying to determine the sputter run procedures that ensure consistent surface conditions for plasma and the plasma characteristics. This is extremely important to help prevent the surface poisoning that was brought up in the last slide. This was a problem heavily later on in the research, but we will talk about how that slowly was phased out and how we overcame that challenge and the minds behind how we kind of fixed that. Choose sputter run constants and variables for experimental treatment, experimental design, varying sputter ambient, and annealing with oxygen. Characterizing IWO film properties by measuring sheet resistance and optical constants, and evaluating the semiconductor behavior via TFTs. So what kind of characteristics are we looking for in our devices? Well, we don't want something that acts like a metal. We want something that acts like a semiconductor. So this is what a metal would give out in a IV curve, where there's no observable gate modulation. It's always on but never off. Here we have an insulator, and again, this is not what we want. We want some sort of modulation. So for a dielectric or an insulator, this is always off but never on. So moving on to the next slide, we can see that this is exactly what we want. We want something that has a depletion mode and something that has electron accumulation. This shows that there is modulation and that there's a gate where it can turn off and turn on and give a proper transistor behavior. So in our findings, what we had in our preliminary research is this. We have a unpassivated thin film transistor done back in November of 2020. We used unpassivated 15-15 argon to oxygen ratio, which is a 6.7% oxygen ambient with a 2-hour anneal at 300 degrees C. This was our best TFT that we had at the time, and from here we wanted to make this a repeatable process. Something to note is that this is encouraging, and that we want to be able to repeat this now, and we want to see if we can make it better. But like I said before, we ran into some target poisoning due to what we think is a non-stoichiometric metal oxide forming on the surface, which would then create a insulating type behavior once it was actually sputtered. So we were actually getting these awful curves that just yielded us with no real reasonable data, and we didn't know why. until we decided to look at the target and find out that it is green and has this green circle around it in the center and a very pronounced racetrack, much different than what is it's supposed to look like. So after some brainstorming and creating a flowchart, the target looked like this after several runs without it really being taken care of or us really having an idea of what was going on. And we were running this at 50 watts. We were getting constant current of 1.3 amps and volts coming out to be 39 volts. After reconditioning and sanding it down, we decided to do a 1 hour argon sputter with no oxygen, and then found out that we can do a 30-minute pre-sputter with no oxygen and yield it looking the same. Initially, it was 1.3 amps with 39 volts, but then it ended up, interestingly enough, at 0.15 amps at 330 volts. As to why this happens exactly, we don't know, but further investigation, I'm sure we'll eventually be able to get to a conclusion for this. Creating this flowchart helped us keep our target free of surface contamination, or surface poisoning rather, and we figured out a good way of getting our data to where it needed to be so that we can achieve repeatable characteristics like we saw earlier for our preliminary results. So how do we make good data? How do we decide on what kind of conditions and variables and constants we need, and what needs to vary in order for us to see data worth capturing? So we decided on making some sputter conditions exactly the same each time we do them, and what we can see here is that there was 50% DC, 50 watts DC sputter, pressure 7 millitorr, overnight pump down on our rotating platen on the CVC 601, pre-sputter time of argon only for 30 minutes, and a sputter time of 30. Something to point out is our argon oxygen ratios that we decided and how we captured that data. The argon MFC is 280 skims, and the oxygen MFC is 20 skims. So we want to observe the volume percent oxygen within the chamber while we're doing our sputter. And that's exactly what we could see here. You take the argon percentage, oxygen percentage, add them together, and then divide by the oxygen, and then you'll get your volume percent oxygen within the chamber. So this data was captured from one of our best wafers that we did TFTs on and took the material samples with. We have a spectrum from 4,000 angstroms to 5,000 angstroms. This is how our vase, which is ellipsometry, finds the thickness as well as the refractive index and extinction coefficient. So as we can see, we have two graphs down below, both of them plotted against wavelength. One is index of refraction and the other one is extinction coefficient. And what we can see is as we go up in wavelength from 4,000 to 5,000, we see a clear increase in our refractive index, whereas our extinction coefficient decreases significantly from 4,000 to 5,000. One thing to note is how our anneal affected the extinction coefficient and how it made it a lot more linear than it did curved, and how there are pros and cons to having a high extinction coefficient and low extinction coefficient, but just something to note there with annealing and how important that ends up being later on. Here we have the optical versus percent oxygen graphs that we use to plot against each other. This is at 400 nanometers, and what we can see from here is as our ambient oxygen went up, we had a increase in refractive index. And but interestingly enough, as we increased our oxygen, we got a lower thickness value. Looking here, we could see our ResMap data and our van der Pol data that were measured concurrently, where I used a ResMap, and with the TFTs we used van der Pol test structures to see if we were getting similar results on the ResMap versus the van der Pol data, which that data did turn out to be accurate with one another. Finally, getting to some more exciting results, we can see that after a 2-hour anneal plus an 8-hour anneal gave us incredibly good modulation where our device turned on and turned off. And what we can see on the right is before the anneal, this was acting quite metal-like, which is, again, not something that we'd want. However, after annealing extensively, we eventually came to the conclusion that this is definitely capable of acting like a semiconductor, which is what we can see with our 1.25 volume oxygen percentage. This was the first time we were able to reproduce something similar to our findings back in November, and this will continue to be researched so that hopefully we can get better curves, and hopefully this could be a material that could help push us towards a good TFT material for display applications in the future. So overall, we were able to determine the best procedures to accurately ensure that there's no surface poisoning on the target, selected variables that helped best characterize this film, and this was by comparing a lot of things to the volume oxygen percentage and discovering the relationships between N and K values with the increasing of wavelength, and able to produce TFTs that modulate current. However, more testing needs to be done, more processing needs to be done for different annealing to hopefully get our annealing time down from 10 hours to maybe 5, just experiment with different temperatures, and continue to look at our volume oxygen percentage.